All right. I've said that radians are the mathematician's angle, and today we'll find out why. Radians are beautiful. They're so great. They're perfect. They're unitless, as I said, but there's many reasons that mathematicians fall in love with radians. Not bad. Not bad. Let's take a look at exactly why. All right, so we've talked about a couple things from geometry, and let's review some more geometry things. A lot of times we'll have a circle, and we will want to know what is the length of an arc we've talked about. So in geometry, the way I've taught this is you want to know this arc length. You have to know what this angle is here, theta. Remember, that's the central angle. And you have to know the radius. And you have to know how to find the circumference. That's the entire distance around. And you can do this with, you can kind of set up a proportion. You can say circumference is to 360 what that arc length, let's call it S, is to theta. And now if we solve that for S, multiply both sides by theta, you get theta times the circumference over 360 equals S. And that's nice. What is circumference? Circumference is equal to 2 pi r. So I'm just going to replace circumference with 2 pi r. And I get theta times 2 pi r over 360. Great. And if we look at just that equation, we can, and that's equal to S, we can see that there's a factor of 2 here and here, so we can reduce, and we get theta times pi times r, all divided by 180. And yes, I wrote that out with some spaces for a reason. If you look at theta, if that's measured in degrees, that's what we were talking about, right? We said 360 degrees. If that's measured in degrees, and then we multiply by pi over 180, what that does right there is that changes theta to radians. And so if I just do the calculation and I say theta is in degrees, but then I change it to radians, I get this really nice formula that says S is equal to theta times r. And how beautiful is that? So I usually change it and say S is equal to r theta, but what a wonderful equation. So simple, easy to remember, and we can use it to find the length of any arc of a circle. Let's take an example. Geometry problem used to be, and we'll do an easy example so we could do this in our heads. Geometry problem used to be find the length of this arc. And you would say, okay, let's do an easy example where this is 90 degrees and the radius is 4. Well, that's easy because we know the circumference is 2 times pi times 4 centimeters. Sorry, I should put units. So that's 4 centimeters. And that means the circumference is 8 pi centimeters. And most of you would just do this in your head. 90 degrees, that's a quarter of the circle. So a quarter of that would be 2 pi centimeters. That would be the length of this arc right here. Okay, that works. With radians, you did this, 90 over 360, right? That's the fraction of the circle, then fraction of the circumference. With radians, we would change 90 degrees into radians. You could do that by multiplying by pi divided by 180. 90 goes into 180 2 times, so you get pi over 2 radians. That's 90 degrees. And then you could say S is equal to R times theta. So for us, that would be S is equal to 4 times pi over 2. Remember, that's in centimeters, 4 centimeters. And you would get 2 pi centimeters, the exact same thing. Again, pretty easy example, but really nice for mathematicians to know this formula, S equals R times theta, where S is the arc length, R is the radius, and theta is the central angle, but it has to be measured in radians or it won't work. I'm going to ask you to find arc length of circles in our next classroom lesson, and you can do it multiple ways as long as you show your work. The two ways are the way we learned years ago in geometry. So that's to say the length of an arc S is equal to theta divided by 360 degrees and then multiply that by 2 pi r. So you could show that work. That's where theta's in degrees. Or you can use what I've just been talking about, which is S equals R times theta, where theta's in radians. Radians. I think this is a lot easier to use and to remember. Okay, another formula from geometry that looks different when we talk about theta and radians. Again, we've talked about circles. We're talking about circles a lot. If you have a circle, and then you have what's called a section or sector of a circle, like a piece of pie, and you want to find that area, just the area of that sector, not the whole circle. In geometry, very similar to what we did with arc length, you've got a central angle there, and you would say theta is to 360 what the area of the sector is to the whole circle, which is pi r squared. We're going to do the exact same thing. I'm going to call area of the sector A. I'm going to multiply both sides by pi r squared, and so I get theta over 360 times pi times r squared. And similar to what we just did, I'm going to rearrange the multiplication here so that I can change theta into radians. Not as easy to see, but what I'm going to do is I'm going to take this theta over 360 and I'm going to write it this way. Theta times 1/2 times 1 over 180 degrees times pi times r squared equals a. So all I'm doing is just expanding this out, rewriting it. You may not think that's simpler, but let me show you why. If I look at this right here, 1 over 180 times pi, that's pi times 180, or sorry, pi divided by 180 degrees. That's the conversion from changing theta into degrees. So if I change my order of multiplication, if I do 1/2 times theta times pi over 180 times r squared, that changes theta, which was measured in degrees, into radians. And so another way to talk about this formula is to say that, let's see if that works, great, is to say that 1/2 times theta times r squared equals the area of the sector of a circle. Again, it's another formula, but it requires that theta is in radians. And now we can find the area of a sector of a circle pretty easily. Nice thing about radians is we don't have to write those units, right? I've said it a couple times in these videos. Radians are unitless. So if I give you a problem, let me take a look here. We'll just make one up. I want you to find the area of a sector, and I'll give you the measure of the central angle and the radius. So we have a circle. Here's the central angle. Here's theta. Theta, I'm going to say, is equal to 3 pi fifths radians. And the radius of the circle is 10 centimeters. Now all I have to do to find that area is to say that area equals 1/2 r squared theta. So that's a little bit different from if we scroll down here. I said 1/2 theta r squared. I might say 1/2 r squared theta. Same thing. Now I'm going to plug in 10 for r and 3 pi fifths for theta, because that's the radian measure. And so when I do that, I can say that the area is equal to 1/2 times 10 centimeters squared times 3 pi over 5. Multiplying this out, that is equal to 1/2 times 100 times 3 pi over 5. I'm moving the units out here. Centimeters times centimeters is centimeters squared. 5 goes into 100, 20 times. 2 goes into 20, 10 times. I'm left with a bunch of 1s in the denominators, and 1 times 10 times 3 pi, and I end up getting 30 pi centimeters squared. Good. We'll practice using those two formulas in class tomorrow. Those two formulas are, first one, S equals r theta. S equals r theta. And the other one is A equals 1/2 r squared theta. This is used for arc length. Oh, I'll do this. I'll put it back in purple. This is used for arc length. And so our units will be centimeters, inches, feet. And over here, this is used for area of a sector. And our units will be centimeters squared, inches squared, feet squared. Okay, thanks for watching.